Stars are immense balls of burning gas. They are scattered throughout the vast expanse of the cosmos. These celestial objects are the building blocks of galaxies. Stars are responsible for creating and distributing heavy elements. Stars emit light and heat, making them visible across incredible distances. Their energy influences the evolution of planets and the formation of life. Understanding stars helps us unravel the mysteries of the universe. Stars are born within massive clouds of gas and dust. These vast regions, often spanning light years across, are the nurseries of the universe. They are filled with the raw materials needed to create new stars. These clouds, known as nebulae, are the cosmic cradles of star formation. Nebulae come in various shapes and sizes, often illuminated by the light of nearby stars, creating stunning cosmic vistas. They are composed primarily of hydrogen, the most abundant element in the universe, along with traces of other elements and molecules. Gravity pulls the gas and dust together, causing the cloud to collapse. This process can take millions of years, as the particles within the cloud slowly move closer together. As the cloud collapses, it begins to fragment into smaller clumps, each of which can potentially form a new star. As the cloud collapses, it heats up, forming a hot, dense core called a protostar. The temperature and pressure within the core continue to rise as more and more material is pulled in by gravity. This early stage of star formation is crucial, as it sets the stage for the birth of a new star. Protostars are not yet true stars, as they lack the nuclear fusion that powers mature stars. At this stage, the protostar is primarily powered by the gravitational energy released as it continues to contract. The core of the protostar is still not hot enough to initiate the fusion of hydrogen into helium, the process that powers most stars. Protostars continue to gather material from their surroundings. This process, known as accretion, allows the protostar to grow in mass. The surrounding gas and dust form a rotating disk around the protostar, feeding it with the material needed to reach the next stage of its evolution. As they grow, their cores become hotter and denser. The increasing pressure and temperature within the core are critical for the next phase of star formation. The protostar's core must reach a specific threshold to trigger the onset of nuclear fusion. Eventually, the core reaches a critical temperature and pressure, igniting nuclear fusion. This marks the birth of a new star. The fusion of hydrogen into helium releases a tremendous amount of energy, causing the star to shine brightly. This process will continue for millions to billions of years, depending on the star's mass, providing the light and heat that sustain life in the universe. Once nuclear fusion begins, a star enters the main sequence. This is the longest and most stable stage of a star's life. Our Sun is a main sequence star, and it is about halfway through its main sequence lifespan. Main sequence stars fuse hydrogen atoms into helium in their cores, releasing an enormous amount of energy. This energy is radiated outward as light and heat. The color and brightness of a main sequence star depend on its mass. Massive stars are hotter and brighter, burning through their fuel quickly. Less massive stars are cooler and dimmer with much longer lifespans. The main sequence phase is a period of stellar stability where stars spend the majority of their lives. During this time, they maintain a delicate balance between the gravitational forces pulling inward and the pressure from nuclear fusion pushing outward. This balance ensures that the star remains stable, neither collapsing under its own gravity nor exploding outward. The surface of a main sequence star can be quite dynamic, with solar flares and sunspots indicating the intense activity within. Main sequence stars come in a variety of types, from small, cool red dwarfs to large hot blue giants. Each type has its own unique characteristics and lifespan. Red dwarfs, for example, are the smallest and coolest of the main sequence stars. They burn their fuel very slowly, allowing them to live for tens to hundreds of billions of years. On the other hand, blue giants are much larger and hotter. They burn through their fuel at a rapid pace, resulting in much shorter lifespans, often just a few million years. In star clusters, we can observe stars at various stages of their life cycles, including the main sequence phase. This provides astronomers with valuable insights into stellar evolution and the processes that govern the life and death of stars. Understanding the main sequence phase is crucial for comprehending the broader life cycle of stars. It is during this phase that stars build the elements necessary for the next stages of their evolution, ultimately leading to their transformation into red giants, white dwarfs, or even supernovae. As we gaze up at the night sky, the steady glow of main sequence stars reminds us of the incredible processes at work in the universe. These stars in their maturity are the backbone of galaxies, illuminating the cosmos with their enduring light. As a main sequence star ages, it eventually exhausts the hydrogen fuel in its core. Without hydrogen fusion, the core contracts and heats up, causing the outer layers of the star to expand and cool. The star becomes a red giant. Red giants are much larger and cooler than main sequence stars, giving them a reddish appearance. Betelgeuse, a bright star in the constellation Orion, is a red giant. During the red giant phase, stars fuse helium into heavier elements, including carbon and oxygen. Section 5. White dwarfs, stellar remnants. Eventually, a red giant sheds its outer layers. This leaves behind a dense, hot core called a white dwarf. White dwarfs are about the size of Earth. They are incredibly dense. White dwarfs no longer produce energy through fusion. They gradually cool down. Over trillions of years, they will eventually fade away. Sirius B, the companion star to Sirius, is a white dwarf. Section 6. Neutron stars, the cosmic lighthouses. When a massive star runs out of fuel, it collapses. This collapse is very rapid. The collapse triggers a supernova explosion. The core of the star is compressed even further. This forms a neutron star. Neutron stars are incredibly dense. They are only about 10 to 20 kilometers in diameter. They rotate rapidly. They emit beams of radiation. These beams sweep across space like a lighthouse. Pulsars are a type of neutron star that emits regular pulses of radiation. Section 7. Black holes, the cosmic abyss. If a star is massive enough, its core will collapse. This collapse continues indefinitely. This forms a black hole. Black holes are regions of space-time. Their gravity is so strong that nothing, not even light, can escape. Black holes are invisible. Astronomers detect them by their effects on nearby stars and gas. Sagittarius A*, the object at the center of our galaxy, is a supermassive black hole. Section 8. Stellar classification, deciphering the stars. Astronomers classify stars based on their characteristics. These characteristics include temperature, luminosity, and spectral lines. The most common classification system is the Morgan-Keenan, or MK system. The MK system assigns a letter to each star. The letters are O, B, A, F, G, K, and M. O stars are the hottest, M stars are the coolest. Our Sun is a G-type star. Section 9. Examples. Across the cosmos, from our Sun to Betelgeuse. Our Sun is a yellow main-sequence star. It is of average size and luminosity. Betelgeuse is a red supergiant star. It is nearing the end of its life. Sirius is a binary star system. It consists of a main-sequence star and a white dwarf. These examples highlight the diversity of stars. Each star type plays a unique role in the universe. Section 10. The circle of stellar life and death. Stars are not static objects. They are constantly evolving. The life cycle of a star is determined by its mass. Massive stars live short, brilliant lives. Lighter stars burn slowly for billions of years. The death of a star can be a spectacular event. Supernovae and the formation of neutron stars and black holes are some of the most energetic events in the universe. The material ejected from dying stars enriches the interstellar medium. This material forms new generations of stars and planets. Section 11. Conclusion. Our place among the stars. As we reach the end of our journey through the cosmos, it's time to reflect on the profound significance of our place among the stars. Stars are fundamental to our understanding of the universe. They are not just distant points of light, they are the beacons that guide us through the vast expanse of space. They provide insights into the laws of physics. By observing their behavior, we unlock the secrets of gravity, thermodynamics, and nuclear fusion, which are the very forces that shape our reality. They drive the evolution of galaxies. Stars are the engines of cosmic change, influencing the formation and transformation of galaxies over billions of years. They create the elements necessary for life. Through the process of stellar nucleosynthesis, stars forge the elements that make up everything we know, from the air we breathe to the ground we walk on. By studying stars, we gain a deeper appreciation for our place in the cosmos. Each observation, each discovery brings us closer to understanding the grand tapestry of the universe. We are all made of star stuff. The very atoms in our bodies were once part of ancient stars, connecting us to the cosmos in the most intimate way. The atoms in our bodies were forged in the cores of stars billions of years ago. This cosmic heritage is a reminder of our shared origins and the interconnectedness of all things. The universe is vast and awe-inspiring. Its sheer scale and beauty are a testament to the wonders that lie beyond our planet, waiting to be explored and understood. Stars are a reminder of the beauty and wonder of the cosmos. They inspire us to look up, to dream, and to seek answers to the most profound questions about our existence and the nature of the universe. If you enjoyed this video, consider subscribing to our channel. Until then, see ya.